Hello everyone, welcome to this lecture number 36 of the NPTEL course on Riemannian geometry. So last time we derived some consequences of the first variation formula. So we saw that the critical points of the energy functional have to be smooth geodesics. So as a consequence of that, if you have a length minimizing curve connecting 2 points and let us say you parameterize it so that it has constant speed, then it turns out it has to be a geodesic, right, because it's a critical point of the length functional, but because the speed is constant it will also have to be a critical point of the energy functional and hence a geodesic. On the other hand, the converse is not true, as we saw in this example with the sphere, that you take let us say the point P to be the north pole, then we know that all the geodesics are basically these great circles. So let us take this great circle which I have drawn in pink. So you connect the north to the south pole and then you go from behind the sphere to again the north pole. Now let us say your point Q is a point on the other side of the sphere, right. Then clearly the curve shown in bold pink is the curve shown in bold pink is clearly a geodesic, right. On the other hand, it is not length minimizing, because the length minimizing geodesic is going to be the geodesic from the back side of the sphere, right. So clearly being a geodesic does not imply that the geodesic actually is length minimizing. On the other hand, you see that even for this geodesic, if you take points that are close to P, so in fact in this case if you take points from P all the way up to the south pole, the geodesic will continue to be minimizing. So locally near P your geodesic is actually minimizing, okay, even this bold pink geodesic. So that is the sort of general fact that we next want to prove, that geodesics are at least locally length minimizing. So the main tool in helping us prove this is the so called exponential map, which has a lot of other uses too. So the aim of today's lecture is to explain what this exponential map is. Okay, this is going to be a crucial a key construction. So we begin with a proposition. For all points P in M and for all capital T bigger than 0, there exists a neighborhood U of P and a constant eta which depends only on little p and capital T, such that for all points Q in the neighborhood and for all points all tangent vectors at that point Q, such that the length is not too large, the length is less than eta, the unique geodesic gamma v with the initial conditions that gamma v at 0 is Q and gamma v prime at 0 is V. This exists at least for on the interval 0 to capital T. Okay, so in other words, if you remember we had made this remark after our main sort of existence uniqueness theorem for geodesics, that for any geodesic with initial conditions Q and the velocity vector being specified as V, there is a unique interval which is sort of the maximal interval of existence of the geodesic, which we are denoted by IV. So what this says is that this set is contained inside this open interval of which is the maximal interval on which gamma V exists, okay. So in other words, the statement is that if you want to specify a capital T for which you want the geodesic to exist, then there is a constant eta, so that if you take vectors that are shorter in length than eta, then the corresponding geodesic will indeed last for time capital T. Okay, so in particular we are really interested in one special case. In particular, for all points P and M, there exists a constant eta P strictly positive, such that for all vectors V in the tangent space at P, gamma V exists on at least the unit interval, okay, or equivalently the unit interval is at least contained inside IV. Okay. So, the proof I will leave it as an exercise, and the hint is that you have to apply main existence uniqueness theorem of geodesics with the rescaling trick. Okay, so I will leave this as an exercise because I think it's a good exercise to test whether you really understand the existence and uniqueness theorem for geodesics and the rescaling trick. So right, even the rescaling trick is an important trick, so this is a good place to really try to write down a complete proof of this proposition. Okay, but then the proposition allows me to define the exponential map. So before that, let me introduce certain notation. So I will denote the usual projection map from the tangent bundle to M by pi, and any element of the tangent bundle I will denote it as psi, and my notation will be I will denote psi as x comma v, where x is some point in M and v is a tangent vector at x. So any element in the tangent bundle is the tangent vector at some point x, right. So my notation will be that I will denote that xi by bracket x comma v. Okay, so here's the key definition. The domain of the exponential map I have used orange color, is defined to be, so I will denote it by script E. So this is the set of all elements of the tangent bundle such that if you look at the corresponding geodesic whose initial tangent vector is given by xi, and so here this is such that the value at 0 is given by the projection of xi, and the velocity vector is given by this tangent vector xi. Then I want this to be defined on 0 1, or equivalently I want 0 1 to be contained inside the maximal interval of existence. So these are all the possible tangent vectors, so that the corresponding geodesic lasts at least for a unit time. Okay. And then the exponential map is defined by, so the exponential map of xi is precisely the value of gamma xi at 1, okay, or the image of gamma of the time 1 under gamma xi. Then sometimes it is also useful to localize this. So, we localize this at a point okay. We do this by denoting epsilon p to be the domain of the intersection of the domain of the exponential map with the so the slice on the tangent space at the tangent space to M at P, and the exponential map at P is defined to be the exponential map on this slice EP. Okay. Right. So, so just as an example, one can actually compute out what this exponential map looks like. So, let us say I take the unit sphere with the round metric, and let us take P to be the north pole, with coordinates 0, 0, 1. Then for any V in the tangent space to S2 at the north pole, one can actually write down what the corresponding geodesic will be. So, we of course know that it will be one of these great circles. With a little bit of thought, one can write down the correct parametrization. So, here I am thinking of the tangent space at the north pole to basically I am identifying it with R2. So, this is the set of all vectors a comma b comma 0, where a b are real numbers. Then the corresponding geodesic, one can just use spherical coordinates and write down a formula, will look like this. Okay. All right. So then the exponential map. So clearly, I mean these geodesics clearly last for all time. So I mean here t could be any real number. So the upshot is that the domain of the exponential map at P is all of the tangent space, and the exponential map on V is just given by gamma V of 1. So this is just precisely, I mean given by A by square root of A squared plus B squared sine square root of A squared plus B squared, B by square root of A squared plus B squared times sine of the same angle, and then cos of the same angle. Okay, so in this case one can explicitly write down the exponential map, and the key point is that the exponential map is defined on all the tangent space. There are however cases where so as a second example, you just take the punctured disk with the Riemannian metric, which is the restriction of the usual Euclidean metric on R2. Okay. Then clearly if you take a point here and a vector in this direction, then the geodesic, which obviously is a straight line because those are the geodesics in R2, then the geodesic will only last up to a certain time, because in a certain finite time it will hit this puncture and then it can't go any further because your domain does not have the origin in it, right. So in this case the exponential map, the domain will be strictly less than the tangent space. Okay. And this also tells you that it is not necessarily a symmetric domain around the origin, right, because if you take a vector in the other direction, at least in this picture you might hit the other boundary much sooner than you hit the origin when you go in this direction, right. Okay. But even so, examples where the exponential map is defined on all the tangent space will play an important role, and that will basically be a notion of what we will call geodesic completeness. So, this will play an important role later on. Okay. Alright, so let me write down a basic proposition, which again I think it is a good exercise for you to prove. So, so this is a basic proposition. First, that this is an open subset of the tangent bundle, okay, and of course it contains the 0 vector at every point in M. Second, for all tangent vectors, if you look at now, there is no restriction on how small the tangent vectors must be, but if you look at the corresponding geodesic, that is given by the exponential map applied to TV, as long as TV is contained in the domain of the exponential map, right. The proof of this is again by our usual rescaling trick, okay. And the third point is that if you localize to epsilon p, this is an open star shaped domain. So, what does star shaped mean? I.e., oh sorry, I forgot one thing. You have the key formula that if you take the right. So, if you now differentiate at t equals 0, then by what I have written that this is precisely exponential of TV is precisely this geodesic, this will be gamma v dot at 0, but by definition that is just v, okay. So, we get this very useful formula, that if you take exponential of TV and compute the derivative at t equals 0, then you actually get back v, okay, right. Then the third point is that EP is an open star shaped domain, which means that so star shaped domain centered at or with respect to the origin. So, it is star shaped with respect to the origin. That just means the following, that if you take a vector v in EP, then this entire set t times v, where t is between 0 and 1, this is contained inside EP, okay. So, that is what being star shaped with respect to the origin means. So, again I will leave the proof as an exercise. These are all very good exercises and highly recommended if you really want to understand what is going on, right. Okay, so I want to end this lecture with a key proposition which I will prove because this is really the crucial proposition related to the exponential map. So, we consider the following map. So, this is from the domain of the exponential map to a product of M. So, phi of xi is precisely the projection of xi to M. So, xi is a tangent vector at a certain point pi of xi. So, the first component of this map is just pi of xi, the second component is given by the exponential map. Okay, so my claim is that phi is a local diffeomorphism in a neighborhood of the origin at P for all P, okay. Alright, so the idea is that if you are looking at the tangent bundle, so if you for instance a corollary is that for all p there exists a neighborhood up such that the origin is contained inside up and the exponential map at p. So I will denote neighborhoods in the tangent space with a little tilde on top. This is a diffeomorphism. So you can always choose a small neighborhood of the origin in the tangent space so that the exponential map is a diffeomorphism onto the image, right. That's just by localizing this proposition at one point. Okay, so the picture is that you have this neighborhood up tilde which is, so let us say p is a point here. So this will now be a diffeomorphism on some neighborhood of p on the manifold, right. Okay, so clearly the corollary follows from the proposition. So let's try to prove the proposition. Okay, so the only way we know how to prove that something is a local diffeomorphism is basically to use the inverse function theorem. So we will use the inverse function theorem. Okay. All right. So let U be a coordinate neighborhood. So let's do the following. So let's do the following. So fix a point P in M. What is our claim? That phi is a diffeo on some neighborhood of 0 p, not in the tangent space at p but in the tangent bundle, okay, to some open neighborhood of the image of 0 p. But what is the image of 0 p? That is just going to be p times the exponential map applied to 0 p, but the exponential map applied to 0 p is just p, right. You just take the constant geodesic. So I have to show that phi is a diffeomorphism on some open neighborhood of 0 p in the tangent bundle to some open neighborhood of this in the product. Okay, that is what I have to prove. Okay, so let U be a coordinate neighborhood containing P with coordinates and let us say centered at P. Okay, so that means all these coordinates vanish at P. So then if you take the tangent bundle restricted to U, so you can think of the tangent bundle as simply a product of U cross Rn, right, where the point is that if you are given any xi or rather if you are given any v in the tangent space at some q where q is some point in U, then you can always express this v as summation vi times the standard basis vectors, right, and this corresponds to a point given by x1 of q up to xn of q and v1 up to vn, okay, as a point in u cross r to the n. Yeah. Okay, so so in other words, I can think of x1 up to xn, v1 up to vn as coordinates on the tangent bundle restricted to u. So any element of the tangent bundle restricted to u can be described by this 2n tuple. Okay, next, in order to apply the inverse function theorem, I need to know, I need to prove that the derivative at 0p is invertible, right. So what is the derivative map? That is basically a map from the tangent space to the tangent bundle to the tangent space to m cross m. What is the tangent space to m cross m at p comma p? Well, that is just the direct sum of the tangent space at p, right. Also, by this identification, by the identification above, so what was the identification above? You could take the tangent space restricted to u as basically u cross Rn. Okay, so so in other words, if you take the I mean you can think of this as u cross I mean the points of this are basically q times the tangent space at yeah, okay, let me. So then the point is that if you take the tangent space to 0p of the tangent bundle, by this identification you can now identify this as the tangent space to p to m at p, direct sum the tangent space at 0p to the tangent space at p to m. But because this is a linear vector space, you can also identify this as just this. Okay, so the upshot is that you can interpret the derivative map as simply a map from the direct sum of two copies of the tangent space at p to the direct sum of two copies of the tangent space at p. Okay, so now my claim is that interpreted this way, the derivative map as a matrix is simply given by identity, it has a block form and it is simply given by this, okay, where each of these blocks are sort of n cross n. Okay, so let's prove this. Okay, so there are two types of so again recall that this is given by u cross Rn. So how do you calculate the derivative map? To calculate the derivative map, you take a curve and compute its derivative, right. It's you take a curve, you look at the image of that curve under phi and compute its velocity vector, right. That's the way to consider. So there are two types of curves. Okay, which will give this sort of block diagonal form. So firstly, one can take a curve. So let, or rather I should say that there are two types of tangent vectors in the tangent space to the tangent bundle. So the first kind of curve, first kind of tangent vector is you can take a tangent vector in the u direction, which I will denote by v comma 0, or you can take a tangent vector in the in the Rn direction. So that will be a tangent vector of this form, right. So I want to compute derivatives, the image of the derivative map for both these kinds of tangent vectors. So let us first consider the derivative map applied to 0 comma v, applied to v comma 0. Okay, so in order to do this, we have to take a curve in u cross Rn with the initial tangent vector given by v comma 0. Okay. So what is the best possible choice of a curve? We just take the geodesic in the direction of v. Okay, so this is going to be the derivative at t equals 0 of the image under phi of the following curve. We just take this curve in the tangent bundle. Okay. All right, but then by definition of phi, this is simply the projection to the first component. The second component is given by the exponential map. Sorry, the exponential map acting on 0 at gamma v of t, okay, which by definition is simply gamma v of t comma gamma v of t. Okay, which is simply gamma v dot at 0 comma gamma v dot at 0, which is simply v comma v. So the vector v comma 0 goes to v comma v. This accounts for the first n rows of this derivative matrix. Now let us try to prove that the next n rows are given by 0 comma identity. So for that we need to compute the derivative of the of this phi on vectors of the type 0 comma v. So again we need to consider a path whose velocity vector is given by 0 comma v, a path in the tangent bundle. So a path in the tangent bundle again decomposes as a path in u and as a path in the tangent space direction. So the easiest path to take, because the first component is 0, the easiest path is that you do not move at all in the first component. So you take this is d by dt at t equals 0 of phi applied to the path given by p comma and in the second component, if you have a tangent vector v, the easiest path in that direction is just the straight line path, right. You take this. So this is going to be by definition of phi, this is just going to be the projection to the first component, which is p, and then exponential at p of tv. But the derivative of the exponential map at t equals 0 is precisely given by v, and the first component is a constant, so the derivative of that is going to be 0. So you get this. Okay, so that accounts for the second for the last n rows. Okay. All right. So, so in particular, so this proves the claim but then what is the determinant of the derivative map? Well, that is just going to be 1, okay, which is non-zero. So, by the inverse function theorem we are done. Okay. All right. So, let me maybe end this lecture with the following remark. Just a general remark about exponential maps, that suppose I am given any admissible vector field along gamma, then one can consider capital gamma of ST, which is simply the exponential map at P of S times V of t. Then by definition, if you consider the derivative in the S direction at 0, then by one of our earlier propositions, that is precisely V of t. Okay. So, this gives us a general construction of constructing variations out of variation vector fields, out of possible admissible vector fields along gamma. Okay. All right. So, maybe I'll end this lecture here. In the next lecture, we will actually use this map phi to construct a very sort of natural coordinate system near a point P, which we will call geodesic normal coordinates. Okay. So, those are very useful, that is a very useful coordinate system to work in. So, that will be the content of the next lecture. Thank you for your attention, and I will see you next time around. Thanks.